Welcome to the next lesson. We're talking about polymers today. Now, we've touched on this last week when we did the reactions of alkenes. We're just going to do a little bit more practice and go into a little bit more detail about the conditions and the different names for polymers, and we're going to practice constructing the diagrams today. So before we do, for our retrieval task today, we're going to just go back to what we did last week and look at this equation. So the first thing I want you to do is name the two different structures. So remember, the first thing, the easiest way to do this is to count how many carbon atoms you've got and then look for the functional group. So name the two compounds, then give the name of the product of this reaction, or the product. So if you were to react these two things together, which we did on Wednesday of last week, what would you get? And then draw the displayed formula of this product. So pause the video, and then when you're ready, press play. Okay, so hopefully you will know that you have got ethanoic acid. So you count the number of carbon atoms, that's 2, so that tells you that it's going to begin with F. And then you can see the C double bond or H should tell you that that's the carboxylic acid, so ethanoic acid is the first one. Second one is a little bit simpler in that you've just got your OH on the end, so you know you've got an alcohol. So you've got 3 carbon atoms with your alcohol, so you've got propanol. Now our general equation, carboxylic acid plus alcohol gives ester plus water. So we've got to think about what that ester is going to be called. Now remember, the alcohol gives the first part of the name, and the carboxylic acid gives you the second part of the name. So propanol becomes propyl, ethanoic acid becomes ethanoate, so you would have propyl ethanoate. And what this would look like, so the last part of the question was to draw it out. So remember that even though it comes first in the name, it gets drawn at the bottom right. So all you're doing is you get your ethanoic acid and you take your OH off. That forms in part of the water. And then on your alcohol, it kind of does a mirror image of itself. You take the H off, and it's that O that attaches to the C. Now, technically, it doesn't matter which O stays on. You're drawing it out the same way. We've not used different colours or anything. However, that is the way it happens. The OH from the ethanoic acid is removed. The H on the end of propanol is removed. And then it's the propanol that joins onto the carbon. So, and we end up with propyl ethanoate. So the propanol becomes propyl, and that's the first part of the name, and the ethanoic acid becomes ethanoate. Now I know this is tricky, it's just practice. So we'll do a few more in retrieval in our lessons to come. We're going to use this term a lot, and we talked about it last week a little bit, and we've touched on it about saturation. Now if we look at the definition from the dictionary, saturation or saturated means something is unable to hold anything else. It's full. So if we look at this at the bottom, which one do we think is saturated? And we have touched on this before, and it means absolutely nothing else can join. So then that must mean it's the alkanes. We've got ethane, we've got ethene. And reminding ourselves that, and this was on your questions last week, that saturated means it can hold no more. So all the bonds are single bonds, nothing else can join. If you've got a double bond, you've always got the potential for that double bond to open and the next compound, that whatever it is you're reacting it with, to join the carbons at that double bond. When you've only single bonds, that doesn't happen. So alkanes are very unreactive, alkenes are more reactive. So what we're going to look at is the chemical structure of polymers. We're just going to remind ourselves about that. You're going to practice naming and drawing some polymers from their monomers, and then you're going to apply your understanding to some questions. So make sure you've got those questions from class charts, because that's going to form the final part of the lesson before we go through those answers. So recapping then, alkanes, long chains. They're very useless to us. We can burn them, but remember, the longer the chain, the more difficult they are to ignite. They're very, very unreactive. They don't fire easily. So they're very useless to us pretty much. So we go through this process that turns it into useful alkenes and more useful alkanes. Now, hopefully, you remember that this process is called cracking and takes place under high pressure, high temperature in the presence of a catalyst. And you get these two different products. You'll always get smaller alkanes and alkenes, which are more useful because the alkenes are used for making plastics and the alkanes are used in fuels. So remember we talked about propane and butane that go into gas canisters, and then octane, which is things like petrol, and we can use them and we've got a high demand for them. So it's the plastics today that we're going to focus on and how we actually draw them. We had some practice last week, but we're just going to have a little bit more, and then tomorrow's lesson we're going to talk about polymers in a little bit more detail, the different types of polymers before we look at naturally occurring polymers. So where do we get this name monomer from? And it's really important that you can use the name monomer correctly. So we look at that prefix of mono. So we've got a monorail, a monocle, a monobrow, and a monomer. So mono means one, singular. It's the single thing. One glasses, that doesn't make sense. One rail, one eyebrow, one unit. So polymers are long chain molecules made from joining monomers together. So if the monomer was a paperclip, it's the monomer that is the repeating unit. So one thing that repeats itself over and over and over again. So many monomers join together to make a long chain polymer. So our polymer would be a chain of paper clips. So many small monomers join to make a long chain of polymers. Now we said already that this can happen hundreds, thousands, or even millions of times. So it's not just one or two, these chains are millions of monomers long. So what I want us to think about then, in using these examples, is I want us to think about the names and how we get to those names. Just have a little bit more practice. So I want you to recall from last week how we get the names. So propene, what's the rule that gets us to the name for the polymer? And the bottom three should help you, because what I want you to do on the bottom three is tell me the name of the monomer. So work backwards. Pause the video now and then write down those and we will go through. So propene, hopefully you can remember that all you do is put the word poly in front of it. It becomes polypropene. Butene becomes polybutene. Chloroethene would become polychloroethene. So the monomer can be absolutely anything. It can be something you've heard of, something you've never heard of, and the thing that is repeating goes in brackets and the word poly goes in front of it. Now, sometimes in an exam, they're not too bothered about the brackets, but it is good practice to put it in there because the brackets mean, just like when you're drawing the diagrams, that that's the repeating unit. So if we're working backwards, polyethene would be ethene, polydecene would be decene, and poly 1,2-dichloroethene would just be 1,2-dichloroethene. So it looks complicated, but actually it's really, really easy if you just remember the polymer has poly and brackets around the monomer name. So reminding ourselves, and this is really, really important, that we need high pressure and a catalyst. Polymerization does not need high temperature. Most people, just high temperature is a go-to. As soon as you say what are the conditions, they will automatically say high temperature. Now in this case, it's not, because polymers are plastics, and if you put them under high temperature, most of them melt. So we don't need high temperature, but you do need high pressure and a catalyst. Depending which monomers you've got, depends on the catalyst, but you definitely need high pressure to force these monomers together. So we've seen this example before, but just helping us to draw it out. So we've got 6 monomers there of ethene. Obviously, there wouldn't just be 6, there would be many, many, many hundreds, possibly thousands. And we get this long chain. And if you were to draw all those on, it would take a lot of time to do it, because you could have millions of monomers that each have 2 carbon atoms and all the hydrogens. It would take a long, long time. So we do it in shorthand. And this is what we're going to practice today. And we're going to make sure that we understand the rules. You had some practice in your questions last week. And on the whole, it was done quite well. But some of you just made a couple of really simple mistakes. They're simple to fix with just a little bit more practice. So that's what we're going to do. And we're going to have a look at these rules. So I would advise you to make a note of your rules. So the first thing you do, okay, you remove the double bond from your monomer. So you've still got your carbon in the middle, but it's only got a single bond. So you look at the example at the bottom to help you. So draw the bonds out of the carbon atoms vertically. So instead of them being diagonal on the monomer, they come out vertically. Whatever is bonded to the carbon atoms is drawn in the same place. So you look at your first carbon atom, it's got a hydrogen at the top and a hydrogen at the bottom. You put those on those bonds that you've just drawn. Then the second carbon atom has got a chlorine at the top and a hydrogen at the bottom. So you draw those in. Then you draw brackets around the whole structure. Sometimes you'll see the brackets are square, sometimes you'll see them that they're curved. It doesn't really matter. The brackets are very important though, because they show which bit is repeating itself. So which unit, the whole thing, is repeating itself. Then draw your bonds from carbon atoms through the brackets. So you've got to make sure that those carbon atoms have got 4 bonds. And even though it might seem little, you've got to make sure the bonds coming out horizontally go through the brackets. And lastly, you put your N after the brackets at the bottom to show that the whole structure is repeating. Now, as you can see from your monomer, you've got N at the start. So N just means any number. So if you had 55,000 monomers, you would have 55 of those polymer units, of those monomer units in that polymer. So, but at this time it goes at the bottom. And it's the little things like that, like moving the N and making sure your bonds go through the brackets, that will get you those marks. Now I've seen questions like this where they're only worth 1 mark, and I've seen it where it's worth 3 marks. So it's definitely not something you want to just gloss over and not learn these rules. And in the same way as when you draw your polymer from a monomer, you can reverse the rules and draw your monomer from the polymer, and you're going to have a bit of practice at both. So what I want you to do now, this is your task, you're going to copy and complete the reactions. So for the first 2, you're going to copy it as it is, and next to the arrow, you're going to draw the polymer. Now for this last one, I want you to work backwards and show me the monomer. So what would the monomer look like using those rules that we've just written? So pause the video, and when you're ready, restart it and we can go through the answers. So the first one then, okay, so you've got your N, you've got your double bond, and they've used curved brackets, and that's absolutely fine. But as you can see, the double bond's gone. You've got the 2 extra bonds at either side, you've got your brackets, and you've got the N. The only difference in it being ethene is you've got a CH3 instead of that final hydrogen. But as you can see, everything is in the same place. So the first carbon atom has a hydrogen and a hydrogen. The second carbon atom has a hydrogen at the top and a carbon CH3 at the bottom. Just make sure they're in exactly the same place. If you move things about, you will change that structure. So you need to make sure it's in exactly the same place. Okay, so the next one then, so we've got what's called tetrafluoroethene. So basically tetra meaning 4, fluoro meaning fluorine, ethene meaning 2 carbon atoms. So everything then is the same on the carbon atoms. So it makes it quite easy. So just don't forget your brackets, get rid of your double bond. Each carbon atom has 2 fluorines coming from it and N at the bottom. So finally then, we've got you've got a hexagonal structure on there. Now this is called benzene. If you ever move on and do A-level chemistry or higher, you will come across this a lot. It's a very, very, very useful substance. But benzene attached in this process, so this is a polystyrene. So all we have to do is remove the brackets put the double bond back in and remove those extra bonds and put the N at the front. So nice and simple in this process. So hopefully there you've not had any problems in answering those questions. It's just practice, just in the same way as when we put the names, we just put poly in front of it and put it in brackets. Okay, so what we're going to do now is you need the worksheet that's on class charts, and I want you to answer the questions. And when you're ready, restart the video. We're going to go through the answers, and that'll be it from this lesson. Okay, so the plastic used for shopping bags is made from crude oil. Complete the sentences. The compounds of carbon and hydrogen in crude oil are called hydrocarbons. You could have also had alkanes as your answer for that. You could not have had alkenes. Crude oil is separated into fractions such as naphtha using fractional distillation. Disposable cups are made from coated paper or polystyrene. The diagram shows below represents the structure of polystyrene. Which small molecule is used to produce polystyrene? So obviously yours are underneath each other. I've just put mine side by side, and you will find that it's that one, the second one in your sheet. So just making sure that every carbon atom has exactly the same atom or molecule attached to it. Which process is used to make polystyrene from small molecules? That would be polymerization. Complete the sentences using words from the box. So polystyrene is produced from small molecules called monomers. When polystyrene is made, many styrene molecules join to form large molecules called polymers. That's been cut off for some reason. So the last word is polymers. So the last question, then again, it's a little bit more practice at putting it into, well, it's more practice at drawing these diagrams and just showing that it can be a 3-mark question. So this is this is propene. It wants you to draw polypropene. So remember, brackets, remove the double bond, 2 new bonds, and N. Sorry, it's dropped it off a little bit at the top, but there is your correct answer. So well done for today. If you've got any questions, drop me a line. I know you've struggled with this unit a little bit. Please do contact me if you are struggling, and I will see some of you in school this week.